what we did last time, we introduced this Bernoulli random variable and binomial one, which is a direct extension of this Bernoulli. Two outcomes, either success or failure, each of which happens with a probability of p if it's a success, and 1 minus p, which is the opposite, which is a failure. And we further assume that those triers, if you have more than one, assume to be independent of each other. Notation-wise, we simply say x follows Bernoulli. That's the name of the distribution. And then the only parameter that we need to pay attention to when it comes down to Bernoulli is this little p, which is defined to be probability of success. So that's the notation. Now we went on to figure out the expected value of this Bernoulli with p. It's nothing but p, success probability itself, and variance of this same x turns out to be success probability times the probability of failure, which is 1 minus p. In relation to this Bernoulli, we can easily extend the idea to the case of binomial distribution or binomial random variable. You just get to repeat same type of Bernoulli random variable, Bernoulli event n different times, but still independent triers. So it's the same Bernoulli, but you just keep repeating them until you finish all those nth trier. So we say this n trier, the number of triers is supposed to be n, each of which have success probability of little p. Then we have so-called a binomial random variable, which is nothing but n different Bernoulli random variables. So Bernoulli is nothing but a special case of this more general idea of binomial random variable. Well, when it comes down to those two parameters, the first one gets on this number 1 because you only have a one trier, and then the same success probability p. So either you write it this way, Bernoulli p, or binomial 1 and p. So success probability is the same. We just try it one time and then you're done. It's exactly mean the exact same things. So either the previous one or this one refer to the exact same trial. And then probability mass function of this binomial random variable, since we are dealing with say binomial NP, say x takes on I, any integer between the no success at all, and all of those trials turned out to be success. Anything in between, either n choose I because the order among those I successes out of n, it doesn't matter, we don't pay attention to those specific orderings, just we have to count how many of those possible combinations. So that's nothing but n choose I, but then each of those outcomes, they're like p successes, I different successes, which all independent outcomes, and n minus I failures occurs with a probability of 1 minus p. So putting all those n different elements together, first as many as I successes, and then n minus a, means those failures, you end up with this probability, composite probability. So that was the probability mass function of this binomial n and p. To make sure that this is indeed a valid and legitimate probability mass function, you can easily check that by summing all those possible probabilities over those n plus 1 different outcomes, starting with this 0, 1, and all the way to some number positive n. Using the theorem, so-called binomial theorem in mathematics, can show that that's nothing but sum of the success probability and probability of failure, and then raise it to the power of n because you have this partial sum running up to n, and then you end up with this 1, which indeed shows that this is a valid PMF. Then we try 3 examples concerning either this Bernoulli and binomial. First with the tossing 5 different coins, but each of them is fair, and figured out the probability mass function, and then further we went on to try 2 more examples of how to apply this idea of a binomial random variable to those different circumstances. That's where we start. Just a recap. Now we figure out the mean and variance of this binomial n and p. To repeat n different Bernoulli random variable, Bernoulli events the success probability is supposed to be P. In statistics, you deal with certain random variable x, and then you raise it to the power of k, and then take the expectation of whole thing. This quantity here is a specific name, and the name is called the moment. So these are the important dates. The quiz number 3 next Tuesday. Review for the midterm exam 1 week after, and midterm exam is another week after. So basically all Tuesdays remaining are kind of important. Doesn't mean that you can miss the classes on Mondays. So in statistics, define R dot beta is a short acronyms or random variable, because I won't write it like 10 different times. So raised x(a), define random variable to the power of say k, and then you take the expectation of the k to the x to the k, and this one is called kth moment x. So that's the name. I don't know where this one's coming from. Maybe from physics, but they just started calling that as a moment of this x. So if it's the k exponent is 5, that's the fifth moment of x. If it's just a 1, that's nothing but mean. If it's 2, something related, closely related to the variance of x. So we first figure out what's the kth moment of this x when x follows binomial n and p, and then we can easily extend that to the case of first mean, just simply by plugging number 1 into this k, and then extend it to the computation of variance as well, because variance is nothing more the difference between the second moment of x and the square value of those first moment, which is the mean. Having said all that, kth moment of x when x follows binomial n and p can be written as this partial sum. Where does this one come from? Why on earth this simple notation e to the expectation of e to the kth can be expressed this rather messy form of this partial sum with this rather complicated looking summand, which involve I, k, n, and p, and 1 minus p. How do you know that this first equality is indeed true? What is this part? N choose I times p to the I and 1 minus p to the n minus I. Never seen it before? I saw it a few pages back. I saw it right there. That's where we picked it up. That's a probability mass function. So probability mass function of a binomial n and p. This formula I don't think will be given, because once you know that the number of trials is just n, and each of which occurs with the success probability of little p, you can easily derive this formulation. So this one is either you memorize it or just reason this one out. Just given total number of trials n, assume that you want to have I different successive. Of course, this I is either less than or equal to this little n. Just figure out how many possible combinations of having I successes out of n different trials. That's n choose I. Each of which you have I successes, which means that p to the I, and that n minus I failures, which is the 1 minus probability of that one. So that's nothing but the probability mass function of this binomial random variable. And why do we have this probability mass function of this binomial to the right hand side of this summand? What exactly justifies this equality? So that's a PMF of x, but we want to compute the expectation of x to the kth. Why do we put the PMF of x here? Because of something. something that we did like last week and 2 weeks back. So strictly speaking, expectation of some function of x, if x is a discrete random variable, all possible choices for this x, yeah, that's right, little x belongs to big X. F of x, some mass function, but in principle this one has to be the probability mass function of this f of x. But because of the one of the propositions that we introduced last time, this one is actually the probability mass function of x. There's a big difference whose probability mass function it is. And the definition says that this p of x should be the probability mass function of the entire function f, but the proposition conveniently let us use this probability mass function of x itself. So that's the result of the application of the proposition. So that's what we are doing here. So although what we are trying to get is not the expectation of x, it's the expectation of the real valued function of x, which is x to the kth, still can use the same PMF of x under this convenient proposition that we introduced. So have that summand x to the k, this I is the dummy. If you see a little inconvenient, you can just replace this one by little x or something. It's just a dummy, it doesn't really play any role. Just chose to be I, it necessarily has to be I. So any other letter or character or symbol that you might feel comfortable using it, just to use that. But here I used I, but could be little x. So that's what we're having, I to the kth, because we want to compute or figure out the expectation of this x to the kth. And then rest of them, supposed to be the probability mass function of this entire x to the kth. But because of this proposition, we conveniently replace that one by the probability mass function of this original x. So that's this. Because we know that x is a binomial. Okay, two different things. First, the definition of expectation of something. That's something times that's probability mass function. But because of the proposition, we replace the probability mass function part by the PMF of the x, not the PMF of x to the k. What about the second equality? How on earth can we move from here to down here? What's the difference? Looks almost the same, except for one thing. Yeah, the index starts from 1, not from 0. Why can we exclude the case I equals 0? How come I equals 0 case missing out? What happens if you plug 0 into I? So summation is just the array of like different numbers when you get to plug in each of those possible values for the index into that summand, which is this function. But then if you plug 0 into I here, what happens? So that's a 0 to the kth. What's 0 to the kth? You multiply 0k different times. So if you multiply 0k different times, what do you get? Still 0, so it doesn't count. That's why. So simply rule that one out because it's 0. I mean, if you add 0 to something, it's just still the same something. Doesn't make any difference. And then conveniently use this identity. I times n choose I turns out to be same as n times n minus 1 choose I minus 1. What about this identity? How do we verify it? Where did we get this identity? How do you know that these two things are the same? So n choose I times I is one thing, and n minus 1 choose I minus 1 times n is different. If I ask you to verify, how do you do it? Well, easy way would be stick with the definition. You know what the n choose I is. what we are having on the left hand side so I and there's a factorial. They look a bit confusing. So that's what we're having. But on the other hand, what's on the right? Just using the definition, nothing more. So they look indeed exactly the same. So these are i's, not factorials, right? These are factorials, not i's. I on one hand and factorial like I upside down. So indeed they are the same. Other way just to explain it using the meaning of this combinatorics, but some of you might find it actually more difficult. So simply go with the definition of this combination. Given this identity means some equality between two different things, something like this. We use this property to rewrite this the expectation of the kth moment, not the expectation of x to the kth. So this one is written as that, but because of this identity, we can write the whole thing as this. If you don't see it immediately, let me do it this way. First, write that one on the board. That way, right? Because that one moves over to next page, so it's not like having them side by side. So expectation of x to the k. I running from 1 to n. That's I times I to the k minus 1. Still and choose I. P to the I to 1 minus P to n minus I. Right? So you see that there's I there, there's n choose I there. Put these two things together. So this one here is because of that identity that we just introduced. Replace this and that by this. And then we have one of those p here and then n. Pull those two things out of that summation. Same as that, just that you have to switch this order. That's what you're having. Well, it's just the same thing as your note, in case you didn't immediately see why. Just wanted to put them on the board, nothing more. So that's what we're having. So this one, this messy expression, can be easily shown to be expectation of the k to the x to the k, which is the kth moment of x. And then all of a sudden, something new pops up, which is what's called a J. What on earth is this one? Where do we pick up this J? So far, everything was expressed as like partial sum of those quantity involving this index I. But now we all of a sudden dealing with this so-called J. What is J? Yeah, it's a different index. So defined to be I minus 1. So new index J is defined as I minus 1. Then I is nothing but J plus 1. So replace I by J plus 1 everywhere. So I is there, but just using the second index J, defined as I minus 1, can be easily replaced by J plus 1. And basically another I minus 1 there, so put J instead. I minus 1 there again, so you put J, and I there, and then put 1 plus J or minus 1 minus J there. Same. Doesn't mean anything because index is just a dummy. Whether it's I, J, or K, still same thing. But then the punchline. So having this messy expression in terms of all these J's, we claim that this is nothing but n times p of expected value of y plus 1 to the order of k minus 1 when y indeed follow binomial n minus 1 and p. Where do we pick this one up? How do you know that this is expectation of this stuff? What is this one? We have seen something like that one before. I'll tell you where we saw it. So the place where we saw something like that one before was when we were defining binomial x. That xb binomial m and p, then probability mass function of this might be better, I think. And x running from 0, 1, all the way to n. That's where we saw it. That's a PMF of x. But then what's the highlighted part if this is the PMF of x? So define new random variable, say y. We don't know what that one is now. Just put instead of n minus 1. Still p. Okay. Then what is this one then? If the D1 above is the PMF of x. That's another problem mass function of what? What's y? What's the distribution of y? If the probability mass function y is defined to be this one. If you compare this one and that one, the only noticeable difference is this. Up there you had n, same probability and same probability of failure down here. The only difference is you used to work with this n. Now all of a sudden you have one less than that, which is n minus 1. So it doesn't really change anything. It's still binomial, just a different parameter. Only the first one changes. Still binomial. But instead of n, you have to put n minus 1. But still the same probability of success, which is supposed to be little p. So it's nothing but the probability mass function of another binomial. The only difference between the previous binomial and this newly defined binomial, that the number of trials is one less than the previous amount. But success probability still stays exactly the same. But then, having said that the highlighted, this part is nothing but the probability mass function of another binomial, why do we know that that's the expectation of this y plus 1 to the k minus 1? What really justifies this last equality? Where does this expectation coming from? If this is the PMF of y, such that y is another binomial with n minus 1 and p. Well, if you don't know what to say, just say proposition. It'll be true like half of the time. It's because of the proposition. So proposition, what we introduced, expectation of some real value function of a certain random variable, that's a real value function of y. And in computing that, you just need to figure out the probability mass function of y, not the probability mass function of the entire function. So that's the probability mass function of y, which indeed the same command of j plus 1 to k minus 1. But since this j is a dummy, could be y or x, if you just simply replace this one by little y, that's just the expectation of y plus 1 and to the power of this k minus 1. So it's again the application of the proposition. So is it that quiet? It's because of Monday morning or because of quiz or? There's no life in this class. I'm supposed to tell you some jokes or something? Who didn't pick up this last equality? Who didn't see why this is the expectation of this y plus 1 to k minus 1? So first show that this is the probability mass function of certain random variable, and that random variable is supposed to be another binomial random variable. In binomial, we need to just define two things: how many times you get to try and what's the success probability for each. So we claim that this is nothing but the probability mass function of random variable binomial with the trial number of n minus 1, but still the same success probability of p. So that's a PMF of another binomial. But then because of the proposition, in computing the expectation of certain function of this binomial with n minus 1 and p, we just get to use the probability mass function of this y set, not the probability mass function of the entire function. So that's this. It's a combination of defining another binomial with a different number of trials, and then the same application of the proposition that we have been using over and over again. So that gives us this last equality. Then we are done basically, because once we reach here, all we need to do, what's remaining until we figure out what the solution to this expectation of the x to the k. For the mean, just simply replace this k by 1. So if this indeed the case for the general case of little k, whether we plug in 1 or 10 into this k, this equality should be still preserved, which indeed the case. So replace or plug 1 into this k, that's nothing but the expectation of x, the first thing they want to desire to compute. And then if you plug another 1 into the same k on the other end of this equation, you basically end up with, what do you end up with if you plug 1 into k in here? What does this one become if you plug 1 into k? 1, because something to the power of 0 is still 1. So expectation of 1 is just 1. So you end up with n times p. So that's the expectation of binomial n and p. Okay. So first generalize it to the unknown case of this k, and then first specify it, assume that that's 1, and that will deliver us the value of this expectation of x. variance. So binomial n and p, the expected value of that binomial is nothing but the product of this number of trials and success probability, n times p, as we can see from this one. What about the computational variance then? How can we utilize this convenient general relationship to figure out the value for variance of it? Now plug what into K? So we call the useful formula for the computational variance. So there are two different ways that allow us to compute the variance of certain random variable. First way is just the definition. Second way is just a useful formula, useful fact. It's not the definition though. Same variance can be alternatively computed as first the second moment, because the exponent is 2. And compute the expectation of it, square it, and then subtract that. Right? But given that formula, the kth moment of x when x is a binomial n and p, which way would be more convenient to get the variance? Clearly this one, right? Because we can easily get the second moment using that formula. Simply by plugging 2 into k this time, not 1. So if you put 2 into this k, so that's the second moment, which is the circled one. But then you have to do the same thing, plug in the same number into another k on the right hand side. So that's nothing but n times p times expectation of y plus 1. Right? So that's this. If you set in k equals 2, the expectation of k squared is nothing but n times p times expectation of y plus 1. First equality coming right from this one. Just plugging 2 into this k, here, there, another k there, and that will give us this. How do we move from here to the third one? So that's the result or application of the previous outcome, this. But what about the D1 after this? Where do we pick up this one? We pick up this one. Because the note says so. How do you verify this? I know that n times p times the expectation 1 plus y is n times p times some math system n minus 1 times p plus 1 inside. So another proposition was a linear combination, expectation of some linear combination of certain random variable is a same linear combination of the expected value of the random variable. So remember this one. So we show that expectation of linear combination of some random variable like this, that's the same linear combination. We get replace the x by expected value of x. Right? That was another propositional corollary that we derived last time when we were here. So you're applying this one to first this, but then e over y plus 1 is nothing but e over y plus 1. So because of this, we do have this. Right, quite simple. But then what was e over y? What's this? Anyone? expectation of y when y was this one. What's the expectation of y? Where do we figure out this expected value of y? Or simple, we already know the expected value of this binomial n and p is n times p. We showed it. This is a known fact now. But then what's the expected value of y? Product of these two. Number of trials, which is n minus 1 now, and the success probability. So n minus 1 times p, simply because of this. You get it? So that's where we get this E of y. So first apply the proposition, the linear combination of this one, and then taking the expectation of that. So same thing as first take the linear combination, but what you are taking the linear combination for is not y, but that's E of y. So that's n minus 1 times p. So it's expectation y plus 1. So that's this third equality follows. Okay? But then since we already know expected value of any random variable x with the number of trials n and success probability p, just n times p, go back to the useful formula and let us compute this variance of x in rather easy way. First, second moment, and then square value of this first moment. And then we already figured out the first step, which is the second moment. We just copy it down here. And then the first moment, we already figured it out from the previous page. Plug that one into this bracket and then square it. And if you summarize it well, you end up with n times p times n minus 1 minus p. So that's the variance of it. So mean of any random variable, not random, binomial, it's n times p, and then variance of it on top of this n and p, you multiply that one by probability of failure, and that will become variance of binomial n and p. Right? Quite easy to remember. Binomial n and p, you get to try n different times, each of which has a success probability with little p. Mean is just a product of the number of trial and success probability. Variance of that is just times probability of failure. N times p times 1 minus p. Okay? Will I ask you to derive this variance and expected value of binomial n and p on the exam? Of course not. But you should know this formula. What's the mean and what's the variance? And this one will be used again and again and again as we move through this course. All the time. Literally all the time, until mid-June. Actually, this one will get used a lot more when we have the final, because of this center limit theorem. So one of the most important results that you get to learn in this class is called the center limit theorem. So that one hugely depends on these results regarding this binomial random variable with n and p. Comments or questions or anything so far? Of course not. Just kidding, because it's so quiet. Finally made people laugh. So that's something to accomplish for the day. So we are done with the binomial and Bernoulli. I'm now getting into this third one, which is geometry random variable. This one, in some sense, we already did it. And the example that we tried last time was a coin tossing. You keep tossing some fair coin until you get the first success of this first hat, and then you stop. So that's called a geometry random variable. Why geometric? You saw it. Probability mass function for this geometric x, and when x takes on little x, first you must have x minus 1 failures. That's why this x becomes x. So x becoming the little x just means that all those first x minus 1 tries all fails. and then you have the first success at this little x. So the first half refers to that all x minus 1 failures in before. So that's a 1 minus p times x minus 1 different times. And then you finally close it up with a final success that comes at the x trial. So multiply that one by this p. Finally, you have success at the x trial. So that's the PMF. So simple. Binomial, not binomial, geometric. If the geometric x takes on, say, 10, assume that x equals 10. The fact that you stopped at the 10th trial means that you had the 9 tails in before. And then the 10th trial you ended up with the first half. So the first probability that you need to consider, the previous x minus 1 here, only 9 trials, or all failures, each of which are independent. So that's a failure for each of those 9 cases, 1 minus p, times 9 different times. And then you come back around and try one more time at the 10th trial. Finally, the first success coming through. So that's p. So that's how you formulate this simple probability mass function. But this one, if you look at the shape of this probability mass function, that's nothing but a geometric series. That's why this one's called a geometric random variable. You know what the geometric series is? There's an initial value of x0 or a. You first multiply the first entry by some probability less than 1. So that's the second entry. For the third one, you multiply another p by the same one. So that's a to the times p to the second, which is squared. And just keep going. It's endless. That's a geometric series. So there's a common factor of this little p, initial value of this a. So the stuff that you keep multiplying by, that's called a common factor. P times there, another p times there, another times p, just keep going. So that's a geometric series. And if you look at the structure of this probability mass function, that's exactly that. What's the initial value there? What is a in that case? P. That's p. So the first entry should be the case when this x takes on 1. If you plug 1 into x, you get p. So that's initial value of p. What's the common factor? 1 minus p. Keep multiplying that entry by 1 minus p over and over again. Never stop. So that's a geometric series. So-called a geometric random variable. But this one is a special case. It's just not the series. This is a probability. So if this is a valid PMF, if it's indeed a good probability mass function, sum of all these probabilities must add up to 1. Now we check it. So if you sum up all these probability mass function of certain random variable, starting from the first initial value of 1, all the way to the positive infinity, because it never stops, you literally can continue. You might never have a success, but then the summation, x running from 1 to is positive infinity, using this formula, the probability mass function of x, you can write it this way because this p is completely free of this index x. Pull that one out first, and what's remaining is nothing but the sum of this geometric series. But for this one, initial value is 1, because if you plug 1 into this x, that's a 0. Anything to the power of 0 is 1. So the initial value of 1, but still the same common factor of this 1 minus p. So if you remember the formula, sum of all these entries from high school algebra, this one is defined as the first ratio of initial value, 1 minus the common factor. So if you apply this formula to this one, initial value was p. So initial value is the value that you have when you're plugging in the first number for this index x. So that's p. And the common factor is just this one. Well, actually, the initial value is 1, but you have a p outside there, so that's still p. And common factor is 1 minus p there, so you have to subtract that one from 1. So common factor is p. You have to subtract that one from 1 and put that at the denominator of that fraction. So that's 1. Because one here and another one inside the bracket will kill each other. But there's a change of sign because of two minuses. So end up with P both at top and bottom, and ratio is simply 1. So it's geometric. Now we try one interesting example. Hopefully interesting. Does everyone know what urn is? Have you seen this word before? It's a bag. Just a bag. You know what a bag is? Sack. You put certain things inside. So a bag or urn or sack contains n different white balls and m different black balls. You know what white balls and black balls are. And these balls are randomly selected one at a time until the first black ball appears. So that's exactly geometric series. Geometry random variable. You keep trying until the first success comes out, and the first success definition. So you select a black ball. Well, you have to assume that each one of these balls picked up must be replaced. So this is an experiment with replacement. So you pick one ball out of the bag, check its color, whether it's a white or black, you have to put it back. And then you keep drawing one at a time. So it's like the same trial all over again. So if you pick it up and don't put it back, that's what's called a without replacement. But since you just simply check the color and then put it back to the urn, it's called the with replacement. So number of total balls inside the bag doesn't really change at all. Just keep drawing. This is exactly the geometric series. Because you keep doing until the first success appears. And the success, in this case, is defined to be picking up some black ball. Two questions really. What's the probability that you just get to draw n different times exactly? Have this first one. You keep drawing, but the total number of trials until the first success has to be exactly n, and then you stop. What are the chances? So So total number of balls is n plus m, and then until until you get to pick up the first black ball, you just have to repeat this experiment n different times. So what's the probability of that? So probability of exactly n rows. How do you rephrase this one? You have to pick up exactly n times. So how do you put that in different words? Well, what do we mean by saying that you stopped after the nth pick? When does that happen? You do the first draw, check the color, put it back. Do the second draw, check the color, put it back. Keep doing it until the nth picked, and then you just stop. What does that mean? First n-1 draws are all white. And then you pick up the first black at the end. Right. basically this. First n minus 1 pickup will give you whites, and then the nth one, which is the very last one, will give you the first black. So what's that in probability? Given n different white balls and m different black balls. What's the probability of picking up a white ball? For any random pick. Probability of having a white ball is there. N over n plus n. Exactly. But you have to have n minus 1 different times. Then you finally have the last nth pick black. So that's m over n plus n. So check out the solution. So first define x to be the number of draws needed until the first black ball. And this is obviously geometric with a success probability of m over n plus n. But then the fact that you have to stop at the nth pick just means that this x takes on little n. And that's nothing but first n minus 1 of failures. So you just get to repeat this probability n minus 1 different times. And finally finish everything off with the probability of having the first success at the nth trial, which will occur with the probability of m over n plus n. Just keep saying m and m. Named of chocolates, M&Ms. You know, in my first year at the dorm, when I studied at college in America, the college kids were throwing M&M's chocolate balls. And they're like talking about like a 20-year-old kids throwing the little dots of chocolate. Now the second one, at least k draws are needed. So that's a different outcome. First exactly n draws, and now you're talking about at least at minimum k draws. What's the probability? It's okay to draw k times, it's okay to draw k plus 1 times, just goes on and on, but it's not okay to draw k minus 1 times. The number of draws must be at least at minimum k. What are the chances? So this one. At least k draws. How do you compute this one? So simple way, just first write them all, and then you might be able to pick up the pattern. So it's on the screen, so you can write this one. Probability at least k pickups or k picks goes on and on and on. How can we add these up? What allows us to add up these different probabilities? Someone said something? How can we add these different probabilities? Because these events are it's either independent or disjoint. Which one is it? the fact that we can add these up. These events are independent, disjoint, maybe both, or don't know. Disjoint. So if the events are disjoint, you can add up these probabilities. Nothing in common. It's impossible to have both of these. How can you have like a k peaks and k plus 1 peaks at the same time? Either one of these. So what's the probability of the first? K peaks occurs with what probability? So I'm asking, what's the probability of that? What is this? Well, same as before. K peaks means that k minus 1 failures, and you have a first success at the k prior. So the first failure of a picking a white, and it should happen with as many as k minus 1 times. Then you finally have the first success. Similarly, the second one, k plus 1 pick means first k picks are all white. And then you finally have the first black. Keep doing it. So it's nothing but the sum of this geometric series. If you do it correct, you get this. So x, given that x is a geometric, the success probability of big M over big M plus big N. So the event of interest in this case, this random variable x takes on either k or bigger. So x either equal to or bigger than little k. And that's nothing but the sum of all these. But then the initial value is this one. So that's your initial value. And then you just keep multiplying by the common factor of this big N over big M plus big N. So it's a sum of geometric series. So put the initial value at the top, then subtract 1, subtract the common factor from 1, and you put that at the denominator of the fraction. That will give you the desired probability, finally. Don't get too much discouraged by this second quiz, because I think you can get to drop one of those quizzes. Like we'll have like 6 quizzes, I think, as things are going as scheduled. So only 5 of those 6 will count towards your grade. So every one of you can get to drop the worst performance out of those 6. So you can take this one on as like those 2. I'm not saying you have to drop it, but in case you have to drop, probably this one, because almost everybody got 1 out of 4. Like the 2 or 3 students got 3 and 4. 1 person got everything, but all the rest basically got 1 or maybe 1.5. I was a bit surprised, but TA was happy because grading was so quick. Not many right or question answers in the middle, just either this or that. So just do this or do this. So makes her job extremely simple and easy. I'm not particularly happy about that, but that's what happened. I'll just do this expectation, variance, and star. So if you define this geometric with a success probability of P, what is the expected value of this geometric? This one's a bit complicated, but the derivation itself will not be asked. I just need to explain how we can get this one, but the only thing you need to keep in mind after today's class is just what's the expectation. So E of x, by definition, is this one. All the values taken by this geometric, and then its probability mass function. And PMF we figured out already. So PMF was this one. Find it here. So failure probability first, and then raise it to power of k minus 1, and then times P, which is success probability. But then for convenience, we define this Q, which is nothing but the 1 minus P. It's just the same thing. Notation-wise, it's just somehow easier and more convenient to handle this Q instead of 1 minus P all the time. Nothing really new. Then PMF it just becomes this. Previously, it was just 1 minus P to K x minus 1, but since we are defining this second quantity, just simply Q2 x minus 1 and P. So that's the probability mass function. And if you know calculus, you see that this part is exactly the same as the first derivative of this q to the x. You know this one, right? If you differentiate things like x and 3, x to the 3, which is x cubed. This one you bring down this exponent and make the new exponent 1 less than that, which is this. So I'm just doing this for this one. So if you differentiate this q, if you differentiate this q to the x in terms of q, that's nothing but bring down the exponent first, which becomes x, and then reduce the exponent by 1, and will be new exponent, which is x minus 1. Right? That's just a simple calculus. But then you might be able to switch the order of this first derivative and the infinite sum. So that's only if. We have to check it though. But assume that that's okay. So whether you first differentiate and then take the infinite sum, or just switch the order, first to the infinite sum and then the differentiate it, still have to recheck it. But if that's okay, we can write it that way. But then what's remaining inside this big bracket is nothing but geometric series. Sum of geometric series, because this q is strictly less than 1. So initial value of 1, because if you plug 0 into x, that's q to the 0, that's 1. Just keep multiplying by q. So that's a sum of infinite series, geometric series, which we all know that ends up with 1 over 1 minus q, which is a common factor in this case. But then differentiate the whole thing again in terms of q now, and you will get 1 over 1 minus q squared, and but 1 minus q is nothing but p. So there's a p squared at the bottom. You have to put p, another p at top. So the whole thing, you end up with a 1 over p. So if the geometric series x, you have it, and success probability is p, expected value of that is just the inverse of that, 1 over p. So if you have a fair die, you just keep rolling until you get the first number 3. What's the expected number of trials? So you roll a fair die, 6-sided. Each one of those outcomes are equally likely. So you just keep rolling until you get the first number 3. So what's the expected number of trials? So you first see that that's a geometric series. You keep rolling it. You keep roll a dice until you get the first number 3. So that's a geometric series. Geometry random variable. Success probability is 1 over 6 because it's a fair die. But then what's the expected number of trials? Inverse of that, which is 6, which makes sense. You can have to roll it at least 6 times to get the first number 3. So that's how it works. That's the expected value. Now how to get the variance of it? A bit more complicated. So first go for the second moment of x. Again, define the probability of failure as q. And then by not the definition, by the proposition, expected value of this real valued function of this x, first the summand, which is x squared, and probability mass function of x, not the probability mass function of x squared. So that's a proposition. You still can get to use the probability mass function of x. But then do the similar thing. If you differentiate the x times q to the x, you'll get this. Differentiate this one in terms of q. So bring down this x, which is exponent down, but then you have another x here, so it becomes x squared. Just simply need to reduce this exponent by 1. So that's a q to the x minus 1. Right? So differentiate this in terms of q, you'll get that. P is still there. But then you can pull it outside because it's completely free of this index x. Just a simple stuff like this one again. But then again, assume that it's okay to switch the order of this infinite sum and the derivative. First derivative and then infinite sum might be the same thing as first infinite sum and then do the derivation, not the derivation, derivative, differentiation. But then rewrite the stuff inside this bracket as this. It's just nothing but algebra because you multiply the quantity by something, 1 minus q, and then divide the whole thing by the same thing, another 1 minus q, so they cancel each other. And then if you put this another extra additional q inside, it's nothing but x times q to the x. Just algebra. But then the stuff inside this summation looks quite familiar, and that's nothing but the expectation of x. Right? Why is the expectation of x? Because that is simply p. Right? So that's the expectation of x. So you have a q over 1 minus q and the expectation of x. You see that why this is the expectation of x? If you don't see it, looks like you don't see it. You see it, but you don't seem to understand. So since 1 minus q is p, just simply switch the order. First x, and then 1 minus p to x minus 1, and then p. This is the PMF of geometric p. And then you multiply by x, so that's expectation of x. Definition. So expectation of x, we already figured it out. That's 1 over p. So in terms of q, that's 1 over 1 minus q. In terms of q, I mean. So you have a q over 1 minus q squared, but then you have to differentiate it. And if you do it, you end up with a twice minus p and then p squared. And having this second moment, we go back to the initial first moment, which is expectation of x. Square that and subtract it, and then finally we have this 1 minus p over p squared. So that's the variance. Variance won't get used much, but the expected value of geometric p might be used. Just the inverse reciprocal of the 1 over p. Don't pay attention to those steps that you have to go through to derive this one. Just need to understand what we mean by this expectation of x when x follows geometric p. So that's a 1 over p. In the case of variance, it just get a little bit more complicated, but not that much. Still the same side of the story. 1 minus p over p squared. And when we come back tomorrow, we'll continue with the Poisson random variable, which is last topic in this chapter, and then after that it's basically continuous random variable.